Hello and welcome back. In the previous two videos, we've discussed how you can calculate the size and position of an image formed by a single lens or curved mirror. In this video, I want to discuss how we can calculate the size and position of an image formed by more than one lens or mirror. Now, whenever we have systems involving more than one lens, we need some way to describe which lens we're talking about. And the usual convention is that we say that the lens that is closer to the object is called the objective, and the lens that is further away from the object is the eyepiece. And you very rarely will see problems involving more than two lenses. So the general strategy that we use to solve these types of problems is that you first calculate the size and location of the image formed by the objective. Remember, that's the lens that's closer to the object. You then treat the image that's formed by the objective as if it was an actual object, and then you calculate the size and position of the image formed by the eyepiece using the image formed by the objective as your object. So I feel like the best way to understand how we solve these types of problems is to work through an example. So this example says, calculate the position of the image, the magnification of the image, and whether the image is real or virtual. And we have this lens system here. So we have a lens with a 12 centimeter focal length, that is 36 centimeters in front of the object, and then behind that we have a lens that has a minus 6 centimeter focal length, that is 30 centimeters behind the first lens. So these problems typically take a bit of space to work through, so I'm going to need to open up a blank screen. Now, as usual, I've drawn a picture of our problem here at the top of the screen, and I really recommend that whenever you're working through problems that involve more than one lens, that you actually draw a picture like this, because this is very useful for picturing where the image formed by the first lens is with respect to the second lens. So here we have this object, and it's placed 36 centimeters in front of our first lens, and our first lens has a focal length of 12 centimeters. So remember, the first step in solving a problem involving more than one lens is to calculate the position of the image formed by the objective. Now, one of the things that we need to be careful about when we're working through these types of problems is that we're actually going to have two objects and two images. We'll have the object for the first lens as well as the image formed by the first lens, and then we're going to have the object that we're using for the second lens along with the image formed by the second lens. So we need some way to denote the difference between these two objects and two images. So because this is my first lens, I'm going to call the position of this object DO1. This is the object for the first lens, and I'll call this first focal length F1. And I'll denote the location of the image formed by the first lens as DI1. So if we apply the lens equation to this first lens, we can find the location of the image formed by it. So the lens equation reads 1 over DI1 plus 1 over DO1 is equal to 1 over focal length 1. So if I solve for DI1, I have 1 over DI1 is equal to 1 over the focal length minus 1 over the position of the object. And if I rewrite this with a common denominator, I have the position of the object minus the focal length divided by the position of the object times the focal length. So this means the position of the image formed by lens 1 is equal to the position of the object relative to lens 1 times focal length 1 divided by DO1 minus focal length 1. And if I plug these numbers into a calculator, I see that the image formed by the first lens is equal to 18 centimeters. And you always want to think very carefully about what this number means. Remember that for a lens, a positive value means that the image forms on the opposite side of the lens. So this is 18 centimeters to the right of the first lens. Now the other thing we need to do is calculate the size of the image formed by the first lens. Now I wasn't actually given the size of the object, so we'll just have to settle for calculating the magnification for the first lens. So remember, the magnification is equal to minus DI divided by DO. So this is the magnification for lens 1. So we have minus 18 centimeters divided by, and the position of the object was 36 centimeters in front of the lens. So we see that this is going to be equal to minus 1/2. So my image is going to be upside down and half the size of the object. So now we can go ahead and draw this in here. So this location was 18 centimeters to the right of this first lens. So the image is going to be here, and it's going to be half the size. So we have an image that's kind of like this. Okay, and this is the image that's formed by the first lens. This isn't the final image that's formed by the entire thing, just the image formed by the first lens. Now the second step is that we treat this image as if it was an object, and we calculate the location of the image formed by the second lens using this image as an object. So in order to do that, we need to calculate the distance between this image and the lens, because that's going to be the distance for my object for lens 2. So this distance right here, this is DO2. We're told that the two lenses are 30 centimeters apart, and we found that the image formed 18 centimeters to the right of the lens. So this means that DO2 is going to be equal to 30 centimeters minus 18 centimeters, which is equal to 12 centimeters. So our image is 12 centimeters to the right of the second lens. So we have an we have an object that's 12 centimeters to the left of a lens which has a focal length of -6 centimeters. So now we can find the location of the image formed by the second lens using the lens equation again. So the lens equation again says 1 over di2 plus 1 over do2 is equal to 1 over focal length 2. So again, solving for the image formed by lens 2, actually we can just reuse the formula we found above because it's going to be the same. So it's going to be di2 is equal to do2 times focal length 2 divided by the position of the object 2 minus focal length 2. And now our numbers are a little bit different. The position of the object here is 12 centimeters. The focal length is -6 centimeters. Then we have 12 centimeters here minus -6 centimeters here. And if we plug these numbers into a calculator, we see that this image is going to be -4 centimeters from the second lens. And again, we need to be very careful about interpreting this result. So -4 centimeters, that negative sign means that this image forms to the left of the second lens. So our image is going to be over here. So we have our final image is going to be something like this. And finally, to find the magnification, well, the magnification caused by the second lens is equal to minus di2 divided by do2. So di2 was -4 centimeters, so we have minus -4 centimeters divided by do2, and do2 was 12 centimeters. So we see this is equal to 1/3. So to find the total magnification, and this is something that students sometimes have a little bit of trouble with, so the total magnification, if you think about this, is going to be equal to the magnification of lens 1 times the magnification of lens 2. So the basic idea is if the first image was twice as big as the object, and then the second image doubled that, then your total thing would be 4 times as big. Here, our first lens flipped the image upside down and made it half as big, so our first magnification was -1/2. Our second magnification was +1/3, so our total magnification, if we multiply these two things together, is -1/6. So our image is going to be 1/6 as large as the object, and it'll be flipped upside down. And so this is going to be the last example I'll look at for these types of multiple lens problems. And this will actually be the last topic that we talk about before our next test. So our next test is going to cover wave phenomenon, interference, as well as geometric optics, so Snell's law, lens equation, mirrors, all of that stuff.